So our last video for this unit is about spanning sets, and we talked about spanning yesterday. W could be written as a linear combination of the other two vectors that we did yesterday, and so I told you that that was coplanar, and I would model that with a set of meter sticks. So we're going to talk about writing things as a linear combination, we're going to talk about coplanar, and we're going to talk about spanning. So our first example, we're going to go back to two space. So I have vector u, vector v, and vector w. And the first question says, can vector w be written as a linear combination of u and v? Okay. So can I write w as a combination of 1 minus 3? And we tend to use k and l just by convention. Can I do that? So let's try and solve it. We have two, well, I should write this too. We have two things that we're thinking about, the horizontal component and the vertical component, and I'm thinking about those as two linear equations, so two equations and two unknowns. So first of all, if we look at the x component, can I write that as 1k and minus 2l, and at the same time write the y component 37 as a combination of k and l from the y components of u and v. So if I can do that, if that is solvable, then w can be written as a linear combination. So I think I'm going to do the same thing as I did yesterday. I'm going to isolate k, which would be negative 11 plus 2l. Just because that's an easy choice, you can certainly use elimination or substitution. So I'm going to substitute 1 into 2. And I have got 37 equals negative 3 times k plus 7l. Substitute that k value, negative 11 plus 2l. Oops, there's an l. And solve. 37 equals 33 minus 6l. 6l plus 7l. You're going too fast. 7l. So I'm going to subtract 33 from both sides. 4 and put my l's together. I have 1l equals 4. So if l equals 4, then I'm going to substitute l equals 4 into equation 1 since I've already got k isolated. K equals negative 11 plus 2 times L would be negative 11 plus 2 times 4 would be negative 3. So if K is negative 3 and L is 4, will I be consistent? So I'm going to check with number 1 because it is entirely possible that I have made a mistake. So I'm going to check with equation number 1, left side, whoops, left side is negative 11, right side is k plus negative 2l, which for our values would be negative 3 plus negative 2 times l, 4, which is negative 3, subtract 8, which is negative 11. Left side equals right side. That means that I can write w as a linear combination of u and v. So I have negative 3u plus 4v. So u and v span R2. That means that they can create any other vector in 2 space by having a linear combination of u and v. Since u and v are not parallel, or collinear, then any other vector in 2 space can be written as a linear combination of u and v. Any two non-parallel vectors in 2-space span 2-space. It gets more interesting when we get into 3-space. In 2-space, if we say that vectors are collinear, it means they are parallel. One is a scalar multiple. And they will not span R2. You really only got one vector and a longer one in the same direction, so they would not span. If you have vectors that are coplanar in 3-space, that means they are on the same plane. Any two non-collinear, non-parallel vectors in 2-space, vectors in 3-space, span a plane. Okay? So any other vector on that plane can be written as a linear combination of them. Then we're going to compare linearly dependent vectors and linearly independent vectors. Okay, for 2-space. If vectors are linearly dependent on each other, they are collinear. One is written as a scalar multiple of the other. In 3-space, if vectors are linearly dependent upon each other, one is a linear combination of the other two. In other words, W can be written as a scalar multiple of U and V. That means U and V span a plane. They are coplanar. On a plane. Now, if vectors are independent of each other, any two vectors that are linearly independent, so not collinear, span 2-space. I can find any other vector in 2-space with those two vectors. In 3-space, any three vectors that are linearly independent, I can't write one in terms of the other two, they will span R3. They span all of R3. That means with those three vectors, if they are linearly independent, I can find any vector in 3-space with a linear combination of them.